So how do we go from one coordinate system
to another coordinate system? Let's say that we have a standard 3D coordinate system. We have the x-axis which points to the right, the y-axis which points up, and the z-axis which points forward or backward, depending on whether this is a left or right-handed coordinate system. These axes are of course perpendicular to each other. Let's call this coordinate system our primary coordinate system. The origin of this coordinate system is like the center of the world. And we have another 3D coordinate system, a secondary system, which is different from the primary system and is actually defined in reference to the primary system. This means that the origin of the secondary system is placed somewhere within the space defined by the primary system, and the axis of the secondary system may or may not be parallel to the axis of the primary system. Now, going from the primary to the secondary system doesn't mean that we are actually moving. It simply means that we have a point or a vector which is defined in the primary coordinate system, and we want to get its coordinates in reference to the secondary system. The two sets of coordinates are of course different because the origins are different and the axes are oriented differently. Let's say, for example, that the coordinates of the point in reference to the primary system are 1 on the x, 2 on the y, and 3 on the z. This means that to get to the location of the point within the 3D space, we moved 1 unit along the x-axis, then 2 units along the y-axis, then 3 units along the z-axis. And you can change the order of these steps and you will always end up in the same location. Another way of looking at the coordinate of a point is that it is a linear combination of the axis of the coordinate system in which it is defined. So we have 1 times 1, 0, 0, plus 2 times 0, 1, 0, plus 3 times 0, 0, 1. Now let's do an experiment and project the point on each of the 3 axes and see what we get. The projection in this case is very simple because the 3 axes are of course unit vectors. Their length is 1. This means that we can do a dot product between the point and each of the 3 axes, and this will tell us how far the point goes along the target axis. So we do the dot product and it should not surprise you that we are getting the same steps or offsets along the axis that we initially took to get to the location of the point. Okay, this is very interesting. We can project the point on each of the 3 axes, and this will give us the amount by which we have to move along each axis in order to get to the location of the point. Now let's think about the secondary coordinate system. The axes of this system are also unit length because we can normalize them before we start this calculation. They are perpendicular to each other and they are defined in reference to the primary system. Since the axes are vectors and not points, we can imagine for a moment moving the secondary coordinate system so that the origin of the two systems is the same. Sometimes it's easier to think about it this way. Since both the point that we are interested in and the axis of the secondary system are defined in reference to the primary system, we can do the same projection on the axis of the secondary system, and this will give us the offsets of the point along these axes. And we already know that this basically tells us the coordinate of the point in reference to the secondary system. It's very convenient to package this type of calculation in a matrix. We can write the point as a column vector and multiply it by a matrix on the left. The axis of the secondary system will be written as the rows of the matrix. So the first row is the x-axis, the second is the y-axis, and the third is the z-axis. Multiplying the matrix by the point in this way simply means a dot product between the point and each of the 3 axes. You know that cappuccino in the afternoon is illegal in this country. Don't tell anyone. Now we still need to do something about the fact that the origin of the two systems is different. We say that the secondary system has been translated to some other location. Think about it this way. If the origin of the secondary system is at 1 by 1 by 1 in reference to the primary system, then the origin of the primary system is at -1 by -1 by -1 in reference to the secondary system. This means that we need to apply the reverse translation of the secondary system on the coordinate of every point in the primary system to get it into the secondary system. So the solution to this problem is combined by two transformations. A rotation to align the axis of the secondary system with those of the primary system, and a reverse translation to counteract the translation of the secondary system. The order is critical here. If we do the translation first and then the rotation, we will potentially move in a large circle around the origin of the primary system, and we will probably end up in the wrong location. I actually have a video on this topic, and you can click right here to see it. So we need to apply the rotation first and then the translation. To do the translation, we have to extend the point to a 4D vector and put 1 in the W component. The rows of the rotation matrix are the axis of the secondary system, and we need to extend it to a 4D as well, so we have zeros on all the extra cells except for 1 on the bottom right corner. The translation matrix is very simple. The diagonal is all 1s, and we have the translation vector on the 4th column. We can now combine the two matrices together, and this will give us the final transformation matrix from the primary system to the secondary system. This type of transformation is very useful in 3D graphics, especially when you want to get the location of a point in reference to a moving camera. The only question that remains is how to calculate the axis of the secondary system. Well, turns out I have a video about that, and you can click right here to see it.
Non più tra i farfalloni amoroso, notte e giorno di torno girano, delle belle turbando al riposo, Narcisetto gino d'amor. Delle belle turbando al riposo, Narcisetto gino d'amor.
So the first row is the x-axis. The origins are different, and the two sets of coordinates are of course so that the origin of the since the axes are vectors and not points, we can imagine moving the secondary system so that the origin of the system is the same. Now let's think about the axis of this system. Let's